Hi, I'm Ron Menich from Predictix. Nick Vasiloglu, who you all know and who has been introducing the speaker, works at our other brand called LogicBlocks. LogicBlocks is our platform software brand, and Predictix is our retail application wing. Some of the other members of the team that have worked on this machine learning approach to retail demand forecasting are shown here. We have feature engineers who take data from our retailers and take it in and join it and zero fill it and create derived attributes and do feature extraction and serve it up to the machine learning algorithms. We have algorithm developers, and we have folk who are taking the message of machine learning and putting it in a phrasing that our retailers can understand and digest. Predictix has a number of different decision support offerings. We help retailers model their business in a variety of areas. We have planning tools which enable retailers to determine, for example, their assortment, which SKUs will go to which stores. Merchandise financial planning, which enables them to plan over the future at the department level. Forecasting and predictive analytics that I will talk to you about in greater detail in this presentation. And then supply chain optimization, whereby we write very large math programs to help find out optimal markdown profiles and store and vendor ordering plans that take into account all the factors in the business. Particularly, I'm here to talk about retail demand forecasting and predictive analytics. And demand forecasting is an important thing. Getting it right can translate either into making a lot of money or losing a lot of money. Roughly, in retailing, you can make two mistakes. One, you can buy too much, and then you have excess inventory if it is non-perishable, or you have wastage if you've bought too many raspberries and they go bad on you. On the other side, you can buy too little, in which case you can potentially have lost sales and your customers might go somewhere else. On this slide, we see an example use case of demand forecasting in action at a large retailer that has 150,000 active SKUs and maybe 350,000 seasonal SKUs that come in and out of the assortment at different times of year. They have over 8,000 stores, and each weekend we forecast out to 52 weeks or a little bit more in the future. We crunch a lot of data, and we're a software as a services company. We use the cloud, Amazon Web Services primarily, but we're moving to some other platforms as well this year. So we use elastic scaling of the cloud to crunch the numbers and return them back to user interfaces where the users scrutinize them. The tough problems to solve in forecasting for retailers are those particularly concerned with promotions and price changes, things that tend to jack demand up or down. So that is where sophisticated forecasting can be impactful and can reduce forecast error metrics like MAPE, mean absolute percent error. One of our customers translated that a certain 1% reduction in weighted absolute percent error translates to a 0.75% reduction in inventory, and when you multiply that out, that comes to about $125 million of savings when you do forecasting better by reducing excess inventory. And if you reduce excess inventory, you don't tie up that money, so it can be used for other things, so about 20% of that is recurring benefit. So demand forecasting for retailing is a highly impactful economic problem to solve. Ever since the first shopkeeper in Babylon or opened up their doors, retailers have had to buy product from vendors and put it on the shelf. So this is simply a problem that retailers have had to know from time immemorial. You know, what demand do they expect in the future? And so as soon as computing became available after the Second World War, retailers and the vendors that serve them became very interested in doing demand forecasting. And so the first thing they hit upon was time series models like the Holt-Winters model from 1957, 1960. So retailers have been using computers to do demand forecasting for a long period of time. And in the beginning, it seemed simple. You look at last year's data and you do a little bit of smoothing and there's your forecast. But retailing is quite complex, and that seemingly simple beginning quickly devolved into quite a bit of additional complexity. Time series starts with last year's sales, but within the context of a traditional time series model, it's very difficult to put something like allergy medication that will have peaks in the spring and fall together with sunscreen that'll have a peak in the summertime. So the natural thing that people did was to partition the data and manually decide, well, I need one model for this type of behavior and I need another for another behavior. Within the context of the various time series models, a profusion of models started to develop to handle different data use cases. So some, like Holt-Winters that I described on the previous slide, were for seasonal data. And then others, like Croston's method, were adapted to very sparse data, but had no notion of seasonality. When dealing with a collection of items, some of which are sparse and some not, people came up with a notion that one should aggregate from lower levels to higher levels and then apply models that take into account the law of large numbers at the top level, and then spread those more reliable forecasts down to lower levels. And because the number of algorithms increased over time, people developed these if-then-else rules to decide based on some data conditions which algorithm to apply. And then eventually they started modeling promotions and market mixes and introduced linear regression to the mix. But even after all that, a huge component of forecasting has been the human demand planner who, after seeing the result of all this complexity, has to do a lot of things like inject local market knowledge about events and map new SKUs to existing ones so they can have some history last year from which to forecast. So that simple beginning in the 1950s became a really complex animal. But as I said, retailers they have to forecast. So they use the tools that they had available and actually have refined a lot of these old methods to where in some cases they work okay. But for this crowd, you got to scratch your head and say, really is that all of that complexity with lots of little time series models and if-then-else rules and aggregation and aggregate up and spread down and so forth, is that the best way? And what we've been looking at Predictix in the last year is how machine learning can provide a simpler, modern, theoretically sound, and more extensible alternative for retail demand forecasting. And extensible is of interest because the retail environment is changing quite a bit. Of course, many of you are shopping on the internet and on your cell phones, and as you drive by a certain store, your cell phone beeps because you're getting personalized promotions. All of those types of interactions are changing the nature of the data that retail forecasting systems have to consume. So the problem is becoming more difficult over time, and it needs a new engine. So as I just verbalized, and I'm sure you all understand, causal factors drive retail demand. When it's hot outside, people buy bottled water. When it snows, they buy a lot of snow shovels. Competition is another external factor that can impact your own sales as a particular retailer. If someone opens a store across the street or the competitor runs a promotion at the same time you run your promotion, yours might not be as effective as you might otherwise have thought. And promotions in themselves, if you take a look at a typical weekly circular, they're just wildly multidimensional. They're very difficult to model within typical time series constructs. So you can think about all the different features that you could pull off of an ad here. So show you that computation of the original price minus the $1.50, does that increase demand or not? You know, so retailers are endlessly creative in creating these promotions, and then the question is, you know, how much is it getting them? And so the modeling of promotions is where a lot of complexity comes in and where the time series models start to fall apart. So it should be no surprise that an attribute-based forecast approach based on machine learning is entirely apropos. I think I'm pretty loud, don't you? Is it on? All right. So a modern machine learning approach to retail demand forecasting takes the causal factors or attributes or features or predicates that can move demand up or down and then send it to a machine learning algorithm and utilize the cloud in order to elastically scale the learning computation and throw away the machinery when we don't need it anymore. The machine learning has to understand the direct impact of these attributes along with their interactions, because the way that snow shovels respond to the temporal attribute of Black Friday is different than the way that toys respond to the temporal attribute of Black Friday, right? So it's the interaction between these features that is of great importance. And some of these are just descriptive about the product that is being offered, the product hierarchy, the SKU, the subclass, the class, the department, the brand associated with it, and competitor data. Where is the competitor located? How far away is the nearest competitor? What are the demographics of the zip code surrounding the store? The display and promotions and pricing are the big drivers. You may have heard in retailing, it's all about the product, the price, and the place, right? So promotions can have an absolutely dramatic effect on demand. For some products, the demand when a product is on promotion can be 100x or more of its baseline value. Okay, so if we take all that data and we create attributes, send it to machine learning, then we can get out two basic capabilities. One is, what is our demand going to be in the future, by week or by day going out into the future, and that supports ordering. Ordering from the distribution center or ordering from the vendor in order to position inventory in front of the demand. And then predictive analytics, or what if, which helps retailers to understand how will my demand change if I raise my price, or if I put this product on an end cap display in a store, I move it from the front page to the back page of the circular. So in terms of thinking about the problem, this is a supervised learning problem. In the past, retailers have solved it by a collection of time series methods, but thinking about it in a big data context, it's this supervised learning problem. And then you think, you know, well, what are some appropriate models? You could look at decision trees and random forests and restricted Boltzmann machine or deep learning or whatever. And we looked at the historical models that are used in the marketing mix literature and also used by our company historically, that are typical. Their typical equation is a regression equation like this. It's shown in product form, and you take the log and it becomes a linear regression. And it has various causal effects like promos and price changes and so forth in it. And so what we chose as far as a supervised learning method is a newer method started in 2010 by Stefan Rendel called factorization machines. It is an extension of linear regression. The first part of the equation is just a vanilla linear regression with the direct effects of the attributes, and then the second part includes interactions between attributes, and it can handle two-way, three-way, four-way, and higher order interactions. So linear regression seemed like a good basis by which to choose a method, so we chose an extension of that. This particular method is solved by stochastic gradient methods, or LBFGS, and so it can scale very well, and it can you can choose the batch size that you want to iterate on. And In contrast to something like a random forest, we can also model trend. Trend is a component of many time series models. You know, is demand going up over time or is it going down? And so you want to have some extensibility from the training set into the test set, and that's very naturally modeled within a regression type framework such as factorization machines. Now, the particular problem that we solve when we're doing demand forecasting involves timing. Okay, so if I predict that my customers they want raspberries tomorrow, and I order a bunch of raspberries, but they don't show up until a week from now, then all of my raspberries will go bad. So it's not just that I want to know that my customers want raspberries, I also have to know when they want raspberries. And so timing is an issue that is salient in demand forecasting in a way that doesn't appear as much in recommender systems, for example. Because of that, when we model data, we have a concept of an observation. What is an observation? Well, we look at a product that's on the shelf at a store, a particular SKU for a particular day. So it's on the shelf. Did anyone buy it? How many people bought it? That's our observation. And in many retail contexts, the data is sparse across time. So if you think about walking into a Walgreens store and looking at all of the different types of lipstick or nail polish, all the different colors are different SKUs. Well, someone's going to buy on a fairly regular basis some lipstick or nail polish in that store, but that particular type of lipstick with that color might not be purchased but once in 45 days or something of that nature. And so we have the phenomenon that in our training set, oftentimes 95% or greater of the data is zero. And we need to know about the zeros. We can't just throw them out because we want to understand if there was any reason the demand was zero. In the most extreme case, we could have a high price and demand is zero, and then we put the price down for a promotion, and then we get demand. So we need to know if it was the case that the demand was zero because price was high or some other causal factor was driving that. So just to give you a couple examples of the different dynamics of data, I have some charts, 3 or 4 charts, showing different use cases of demand forecasting. Now, everything I'm showing you is over huge aggregates of SKUs and stores so that you can actually visually see a pattern. As I said, down in the weeds where we actually fit our models, most of the observations are zero, and it wouldn't make for very interesting charts. But when you roll up a bunch of SKUs and stores that are within, for example, a class or category of toys, then you'll see a pattern that looks like this. Toys typically have 70% of their demand or more near Thanksgiving and in the lead up to the Christmas holiday, and then they have fairly trivial amounts of demand elsewhere during the year except when big promotions are going on. In grocery and in many other sectors of retail, there are things called seasonal items. They're only on the shelf for a limited time each year. And then there are very long periods of time when that product is not offered. So in terms of that zero filling that I mentioned, we're only interested in zero filling during times when the product is on the shelf, whereas during periods of time when the product is not offered, that's a null rather than a zero to our algorithms. By contrast, and just to give you the idea here that we're not thinking of an algorithm that just handles sparse data, any retailer has a spectrum of items that go from slow movers, which are the ones that have lots of zeros, to fast movers. And then there are other retail contexts where the decision problem being solved is such that we have very dense data. For example, quick service restaurant. Now, new SKUs can be readily forecasted with machine learning because we can take all the attributes and produce a forecast for them. And as can replacement SKUs. So sometimes we have SKUs that have different packaging and one comes in and one goes out. So there's often a tremendous flux in terms of the thing that needs to be forecasted. And machine learning can help to understand that very well by breaking apart the phenomenon into its attributes. So we've been doing this for a while now, and we're well up on the curve. We've got a couple of customers implementing this, and half a dozen or more proofs of concept that we've completed over the last year. And we continue to refine our capabilities. The zero filling, as I mentioned, is something that we continue to work on, how to use subsets of the training data to have some cardinality control there. The two-way, three-way, and four-way interactions are representable within the model, and the two ways are very direct, and you have to be a little bit more careful with the multi-way interactions. We harness the cloud, as I mentioned, and spread this computation over many, many machines. So we have different learners learning on different subsets of the data, and we have to achieve a consensus amongst those learners as to the parameter estimates. Explaining these results to retailers, as one of the previous speakers mentioned, is always a challenge. And we use a regularization method here, which is something that we want to think about, automated pruning of the long tail of attributes that don't contribute much to the overall demand variance. All right.